This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is to find the shortest distance from A to B on the outside of the box. Intuitively, if we get a rubber band and stretch it from A to B, it should probably look something like this, but we need to find this point of intersection. There is, however, a very simple way of solving this problem. It involves the following trick. Imagine this box is made out of paper, and we take a very thin knife and we cut along some edges and then open the box out. What we end up with is this figure here. The front side here is this bit here, the top face is here, this side bit is here, the back bit here is here, the bottom of the box is here, and this one is the side bit over there. Now that it is flattened out, we know that the shortest distance from A to B is just a straight line. To find the length of this line, we can use Pythagoras' theorem. Here is our right angle. The base has got length 20. This side has got length 4 plus 17 or 21. Therefore the hypotenuse is given by the square root of 20 squared plus 21 squared, which is 29. Therefore this distance here is 29, and the shortest distance from A to B is 29. You may ask though why we are sure the path travels this way and not some other way. Or equivalently, you might say that why did we choose to unravel the box in this particular way and not some other way? Maybe if we cut the box some other way and unraveled it, we would also have a straight line going from A to B that lay entirely on the box, and perhaps it could be shorter. First we add some markings to make this diagram rigorous. Technically, whenever we have got two sides with the same arrow, then we glue them together. So if we imagine this is some paper and we take this edge and glue it to this edge, we're on our way to recovering our box. Notice that the arrows down here and here go in the opposite directions. That's because when we fold this piece underneath, the arrows will then line up in the correct direction. In other words, something on this side of the arrow will be glued to something on the corresponding side of the arrow here. If you take a pen and draw a curve on the box, then when you cut out the box to form this gluing diagram here, you'll still see the curve on it. And the rule is that if the curve comes along and hits this edge at this point, then because that's glued to this edge here, it will then continue on in here. It's a bit like a teleportation. When you hit one side of the figure, you teleport to the connecting edge. Consider taking a very small rubber band and sliding it over the corner of the box. It will therefore form a loop on the box, which looks like this. Indeed, we start here, we go around the side of the box, around the bottom of the box. When we hit this point, we teleport to the corresponding edge here and continue our path. And when we hit this point, we teleport to the corresponding edge and we close up on our path here. Whatever the shortest path is from A to B, it must intersect this curve we've just drawn, intersect this small rubber band we've placed on it. Moreover, if the curve were to wiggle inside this so-called circle, then we could replace it by a straight line segment going from A to the last point that this curve contacted on the circle, and that will be a shorter path. So we now know that whatever the shortest path is from A to B, it's going to start off with being a line segment from A to one point on this curve here. Just to make it clearer, note that this point right here is also A. Indeed, A is at the tip of the single red arrow and the tail of the double white arrow, and this point here is the same. It's at the tip of the single red arrow and at the tail of the double white arrow. We are claiming the straight line path from A to B is the shortest, and by symmetry that's equivalent to the straight line path that goes, rather than going over the box, it goes under the box. When you get to this point here, you teleport to here and continue here. Assumed to the contrary, there's an even shorter path. As we discussed before, it has to leave A and pass through this white curve somewhere, so it can break up the possibilities into several cases. Moreover, it has to travel in a straight line, for otherwise any wiggly section we can cut out and replace with a straight line segment which will be shorter. If we were to leave at an angle just above that of the red line, then once we hit a point which is at right angles to where our red line here meets the point here, once we hit that line, because we then have a right angle triangle, we will have travelled a distance further than the distance from here to here. So any path leaving A at a slightly larger angle than the red path is going to take longer to get to B, if indeed it ever does reach B via wrapping round the box. If we leave at an even greater angle, we are going to hit this edge, wrap around down here to the bottom of the box, and clearly this path is going to be longer than the path from A to B. We know that the distance from here to here is 29, so as soon as we have travelled 29 units along here, we can stop. We know that this path cannot be shorter than the one from A to B. At an even sharper angle up here, we are just going to wrap around more and more before possibly arriving at B. And in the limit, if we head up here, we're just going to wrap around and keep looping around this path. A similar argument applies if we head out in this direction. If we come close to B, then we know that as soon as we have crossed this line at right angles to this direction of arrival here, then we have gone longer than the distance from A to B that we're claiming. And if we go at a sharper angle still, then when we hit here, we're going to wrap around along the bottom of the box. This point over here is also A, and interestingly, we can depart from A and travel in a straight line to B. We again have a right angle triangle, and this time its base is 4 plus 20 and its height is 17, and we can calculate the straight line distance to be 29.41 approximately, making it slightly longer than the path from A to B. If we travel slightly higher or slightly lower than the straight line from this A to this B, then we will travel more than 29.4 units once we hit the imaginary line here at 90 degrees to the imaginary line from this A to B. And if we travel at a wider angle out here or down here, then we're going to wrap around and we're not going to come close to B within 29 units. A similar argument once again applies to trajectories that go close to the dotted line here. And if we wished, we could redraw this diagram to bring this rectangular strip up here and put it down here. In summary then, we are confident that the only straight line from A to B that has the shortest length is the one we've shown here, together with its symmetrical image, the dotted line here. Both these lines have got a length of 29.